Hello again, guys. Review video. Review of some... Oh, actually I should change that. It's not electrochemistry. I decided that thermodynamics was big enough that it warranted its own section. And so this will be just a little review on thermodynamics and some of the ideas we've talked about. And hopefully, by that I do mean review. We may not actually teach you anything here, but we may hopefully remind you of some things that we've seen before. So three important quantities in thermodynamics are the enthalpy, which we actually introduced back in chapter 6, I think. It's the heat, more or less the heat changed during a chemical or physical process, measured in kilojoules per mole. Nature loves things to change in an exothermic way to give off heat. Very common, very favorable for this delta H term to be delta H of a reaction, delta H change in a process to be negative. There's another term called the delta H of formation. If I was making a compound from its constituent elements, then I have an amount of heat associated with the formation of that compound from those elements. And those delta H formations come from tables, tabulated values, or there might be a bizarre one that we don't know and we're asked to find. Also, we may be asked to know that the delta H of formation for pure elements is zero. If I wanted to make hydrogen gas from hydrogen gas, there's no energy change associated with that. The second important term in thermodynamics is the entropy number, and that's abbreviated with an S. It's a measure of disorder. Believe it or not, we can give a number of joules per mole Kelvin describing the absolute entropy or the entropy change during a process for these compounds. And so these are in tables. They're the standard entropies based on absolute zero and a perfect crystal. Let's see, and these are usually positive. I should say the delta S would like to be positive, or Mother Nature prefers definitely to have things become more entropic or more messy or more disorganized. We put the entropy and the enthalpy together and we get this sort of human-made construct called the free energy, or the Gibbs free energy. It's very closely connected to the enthalpy change, but a little bit more than that. So it's also measured in kilojoules per mole. And again, if it's negative, if this comes out negative, this process wants to be spontaneous, wants to go forward in the forward direction. And there's also, in the tables, these free energy of formation. So if I was forming a compound from its elements, I'd have an amount of free energy associated with that. Another definition of free energy is something like the maximum amount of work energy available, extractable from a particular sample. Again, the delta G's are zeros for pure elements as well. Free energies of formation. These equations, very useful sometimes. It's basically products minus reactants, products minus reactants, products minus reactants. So if I have a table with my heats of formation for my products, as well as the heats of formation for my reactants, and I know the stoichiometry balancing the equation, called it M and called it N, or it could be any number, then I just do the products minus reactants deal. Oopsie. And can calculate the enthalpy change, the entropy change, or the free energy change associated with that. How about a quick example of how that might look? Here's an equation. Nitrogen triiodide, 2 molecules of that decomposed to give 1 nitrogen molecule and 3 iodine molecules. I wrote out the delta H, the delta AS, and the delta G for that. So really I should theoretically have this and this and this in a table somewhere. And I just put them together. The 3 goes here, the 2 goes here. So don't forget the stoichiometry. And we practiced this, like I said, way back in chapter 6, I believe it was. And then again in chapter, I have forgotten, 17 perhaps. On thermodynamics, we practice entropy and free energy changes. But if you watch my videos or look at my notes, you'll know there's other ways to calculate this delta G of reaction. Like this. Excuse me. We combine the delta H and the delta S. Again, this one loves to be negative. It's actually measured in kilojoules. If it's negative kilojoules, this is by far the dominant term. this prefers to be positive. It's usually in joules because the entropy change is often a little bit less, quite a bit less than the enthalpy change. This is the Kelvin temperature. I'm subtracting a positive temperature times a likely positive change in entropy, and so I have subtracting a positive term, and therefore this is a negative, preferably. This is a positive, but I'm subtracting a positive, so a negative minus a positive is even more negative. So this really prefers to be negative for spontaneous reactions, and that's reflected here. So if this is negative and this is positive, my free energy will always come out negative, and that says the reaction wants to be spontaneous. We don't really know how quickly it goes forward, but we know it wants to go forward. Similarly, or conversely, if this is positive, and that's not favorable, that's endothermic. If this is negative, that's less entropy, that's not favorable. So the delta G will be positive, the free energy change, positive value, and that's non-spontaneous. Slightly more tricky would be the cases where they kind of compete against each other, in a manner of speaking. Oops, sorry about that. Stay still right there. So if the enthalpy change is negative, that's very good because it's in kilojoules, and it probably will drive this to be negative under normal temperatures. But on the other hand, if this was negative, I'm subtracting a negative term in this right up here. Right, if I'm subtracting a negative, that makes this positive and might detract or lessen from this right here. So at very hot temperatures, it might turn non-spontaneous. This is spontaneous, this is non-spontaneous. Or if the enthalpy change was positive, that's not good. And normal temperatures, the reaction would be not spontaneous, unless the entropy change was huge and my temperatures get pretty warm. Then that might drive the delta G negative. It's like a complicated exercise in positive and negative numbers and this equation. I wouldn't memorize this table, but it's kind of nice to think about sometimes. And remember, the delta G comes out negative, spontaneous, positive, not spontaneous. Negative, it wants to go forward. Negative, it doesn't want to go forward. It would actually rather go backwards. Here's the connection between the free energy under standard conditions and the free energy under non-standard conditions. A little equation. Do you remember Q, the reaction quotient, as described by equilibrium questions, equilibrium problems? It's basically the same as equilibrium constant, products over reactants raised to the power in the balanced equation. But as I've determined this, it might adjust the normal free energy a little bit off of standard conditions. That's a gas constant in energy units because free energy is in energy units. If you used R in joules, then your delta G would be in joules. If you used R in kilojoules, then it would be in, and this comes out in kilojoules. But if this is in kilojoules, you want to use this in kilojoules to make it all match up. Interesting. Just kidding. I'm not giving any examples here very much. I'm just, my impetus, my driving force is just to review a few ideas. Delta G is also tied to the standard free energy is also tied to the equilibrium constant. In the olden days, we said the constant is larger than 1, means it wants to go forward. And if this is larger than 1, the natural log of something larger than 1 is positive. That's positive, and that's a negative though. So my delta G will be negative if this is larger than 1. Saying, again, that it wants to go forward, wants to drive the reaction forward. And lastly, do you remember the heat equation? Very famous for warming up a sample. Could be a solid, could be a liquid, could be a gas, and this specific heat, this C here, this capital C, should be specific to that substance in that phase. M is the mass, usually in grams. For this problem, we often don't have to convert into moles, but got to be careful. If this constant is given to you in moles, or there's some kind of unit in moles, and you may have to indeed change grams to moles, but keep an eye on this constant unit and that. So if this is in grams, and it matches with this grams, and my T is in degrees Celsius, or it could be Kelvin, because the size of the Celsius and the size of the Kelvin degree are the same size. So degrees C or Kelvin, doesn't matter. This is for water, just for reference. But water is really, really hard to heat up and cool off. That's the large specific heat value for any other substance. yeah, so that's how we find the joules. Yeah, this number usually comes out pretty large in joules, and often we'll change that to kilojoules. And it's, yeah, all right. I think that's all I have. Thanks, guys. See you in class. Good luck studying.